thanks again for inviting. It's a pleasure to be here. Today what I hope to do is share with you some of the recent results and hopefully, if I get the time, some ongoing experiments to test Einstein's general theory of relativity at the most strict level. Before I really go into, by the way, can everyone hear me or should I be louder? Okay. Okay. So before we get into the details of what experiments are being done and how we are strictly testing it, perhaps it's good to just take a step back and say why we need to test it in such strict detail. As most of you know, Einstein put his theory of relativity almost a century ago now, and it has been proved so far, or not proved, but its predictions have been verified in numerous cases. It is a physical theory. It tries to explain what's going on in terms of physical events, what's happening. It tries to mesh together, general relativity meshes together the fabric of space-time with how, and its interaction with energy and matter. Like any other physical model, it's judged by the extent to which its predictions match observations. No theory is good if it cannot match what we see. It may be a good imagination in that case, but it's certainly not a physical theory. And a good theory should not only, predict or post-dict what has already been seen, but it should also be able to explain, or it should predict new things which can be either by devising new experiments or looking at other things. It should predict something new and which could be verified. However many experiments you do, you still never really prove a theory. One experiment which goes wrong, definitely goes wrong, is enough to say that, okay, we need to move on to something probably better. It doesn't say that it's wrong, but improvement is needed. Now, these two pillars here are what I would call the pillars of modern physics: quantum mechanics and general relativity. Almost all of what we see is going on can be described in terms of one of these. So they form the pillar. However, there is a problem that quantum mechanics inherently is discrete in nature. The results that you predict, let's say, from quantum mechanics have a discreteness, whereas general relativity, the results from them have a more continuous nature. And the result of that is, while they work very well separately, if you try to put them together, it doesn't go well. They don't mesh well so nicely. And the fact that they don't mesh well so nicely is not a problem in most of the cases. But if you're really trying to push the envelope, trying to answer, let's say, questions like what happened during the very first few moments after the universe was born, then you really need, it looks like from our calculations, it looks like those are the places where both the effects of quantum mechanics and general relativity will be strong enough that you need a quantum theory of gravity, which we still don't have, and we are working towards it. This cartoon, for instance, here, the schematic shows roughly how the universe evolved with time. Any slice, any vertical slice through this tubular thing is supposed to tell you what the universe is at a certain age. The current time is over here, where you see that the tube expands. We are looking at an accelerated expanding universe with stars and galaxies and, of course, us. As you go back this way, go to the left, you're looking at a younger and younger universe, which was smaller, younger, hotter, and so on. And we know pretty well up to, so that the age of universe is currently estimated to be about 13.7 billion years. And we know pretty well with the physics that we have what happened from the, let's say, first microsecond or first millisecond since the universe was born. from that first millisecond onwards up till now, we have a reasonably good idea how things evolved. What we do not is if we want to go further back. That's when, as I was saying, these effects of quantum mechanics and gravity become strong enough that you would need to have a unified theory. That's one of the cases. Another case would be if you are looking very close to neutron stars or black holes. They, again, have very strong gravitational fields. And again, this is a schematic because we do not really have the technology to take an image of a black hole yet, although we might be getting there. If I get the time, I'll get there later. But this is an artist's impression showing how a black hole is accreting matter. Matter is spiraling in. Gas falls into the black hole. And actually, incidentally, not all of the matter that falls in goes into the black hole, but rather we also see some of the stuff is actually ejected out at speeds of light in what's called jets. And that's another area where we have very little idea. But in any case, if you are looking at trying to figure out the physical environment, I'm sure my voice goes ups and down as I turn my head. Apologies. But if you are looking at something that, if you're trying to predict what's going on very, very close to the black hole, there again, both the effects of quantum mechanics and GR would become strong enough that you would need a standard theory, a unified theory. That's why we're testing GR in its strongest possible cases to see if there are any deviations from the predicted or from what general relativity predicts, because those deviations will give us clues towards what the unified model should have as its characteristics. Again, why did we need GR in the first place, or one of the initial successes? Let's look at one of the first triumphs of GR. Again, probably a lot of you are already aware of. Suppose there was a star here, like our sun, and a planet, could be Earth, could be Mercury, one of those. If that was all, there's a star, spherical star, and a planet going around, then according to the theory of gravitation that Newton put forward, this planet would go around the star in elliptical orbit, but in a closed loop. It'll keep going on and on. So it'll always be on this loop, on this ellipse. It'll never deviate from that. And this is something that people checked for planets in the solar system since eons, centuries. And what was found it's most prominent in Mercury, so it was easily seen in Mercury, is that it doesn't follow a closed orbit, but rather the orbit looks something like this, as if it's in an ellipse, but the ellipse is sort of rotating. So this effect is called the precession of the orbits, or orbital precession. It's a small amount, but it was noticeable enough that people knew it from even before GR was predicted. And most of it actually, most of this precession, at least for the case of Mercury, a large fraction of it comes still from Newtonian effect due to the presence of other planets that alter the orbit of Mercury a bit, or the fact that the sun is not a perfect sphere, deviations like that. So detailed calculations, but still within the realm of Newtonian relativity. But even after you accounted for all those effects, it turned out there was a small remainder which could not be explained in any way with the Newtonian physics. People at that point speculated various things like presence of another planet, which was never found. And when Einstein put forward his GR, it was seen that this comes as a natural outcome of GR, this orbital precession. And he showed that when you put in the proper numbers for Sun, Mercury, and other planets and do the math properly, you get the exact period, the exact amount of precision that was observed. So it was one of the first, not predictions, but I'd probably call it a post-diction of GR and one of its earlier triumphs. So that's great. But still, this effect is very small. When you actually look at the numbers, it takes something like 8,300 years for this orbit of Mercury to shift due to GR alone by 1 degree. And 1 degree is a very small angle. I mean, it's very hard to show. It's not that small, but yeah. And possibly, then you'd think that such a small effect could some other theory explain it to as well. Then what you would naturally want is to look for other places in the universe where, say, this effect is stronger. Are there other places where this orbital precession is much larger? In that cases, if we can find something like that, can GR still predict that? That would be a more stricter test. And that's what we try to do. Again, before explaining the test now exactly, let me take one step back and tell you how massive stars which are like 10 times the mass of sun or so, how they end their lives. So it would be a slight diversion in order to get to these tests. If you look at if you could somehow cut open a massive 10 solar mass star which has lived somewhat long, well, you'll notice that here I'm not giving exact numbers, and the reason is not they're classified or copyrighted or anything like that, but these numbers, first of all, there are some uncertainties with the physics involved, but more than that, these numbers also change somewhat depending on what exact masses you take and so on. So I'll be talking mostly order of magnitude here. So a massive star is, let's say, 10 or 15 solar mass. When I say it's reasonably aged, means it's few tens of millions of years old or so. And what's happening let's say, if you could cut open this, then what you would see that it's almost arranged in layers in terms of elements. The lightest elements are on the outermost shells. And as you go inner and inner towards the core of the star, what you have is these shells of heavier and heavier elements. What happens is thermonuclear burning is going on in the star, and in the outer layers, hydrogen is burned into helium, then helium gets burned to carbon, carbon to silicon, and so on, until at the very core, you get to iron. And you stop at iron because iron is something which does not undergo nuclear fusion anymore. It stops there. So you have essentially a core of large iron concentration. That's what you would have for a massive star, its constitution. Now, what keeps the star going? You have fusion going on, basically like thermonuclear bombs, fusion bombs exploding. So that gives you an outward pressure. Whereas the matter that constitutes the star is pulled inwards by its own gravity. So gravity gives you the inward force. The explosions give you an outward force. And they exactly balance to keep the star stable, not blow it up or collapse. This is when the star is going in its normal rate, just like our sun is doing now. But during the later stages of its life, when it has used up most of its fuel, what happens is you have no more outward pressure because the outward pressure from the explosions have ceased. So that now gravity starts winning and the star tries to collapse onto itself, which is shown here, that the core of the star collapses, things are squeezed together. And the weight of the star is so big that the core is at the very center, things are compressed so hard that individual atoms are kind of squished to form neutrons. And as you know, most of the space in atoms is empty. You have a nucleus at the center, and then there are the electrons going around, but the space is mostly empty. If I remember correctly, something like if you would imagine an atom having the size of Empire State Building, that's the size of an atom, and the nucleus is the size of a pea or something. So most of the space is empty. And due to this core collapse, things are squished so much that the atom is, roughly speaking, squished into a single neutron. And the whole thing collapses. And what you form at the very core is is a dense ball of neutrons. As you form that hard, dense neutron ball, then the infalling matter now starts rebounding on that neutron star. That gives an outward shock. And also, as the matter falls in as stuff from, let's say, outer parts of the star falls into here, it releases its gravitational potential energy. It's like, if a brick falls on your head, you get hurt because the brick releases its gravitational energy onto your head. And we don't really, I can't get into that into detail, but you can show that, for the brick or something small, it can hurt, but doesn't feel like that big an energy. But if you have a core like a neutron star here, and if you're bringing something from way far out, you can show that the amount of energy that it released just because of gravitational potential energy being converted, like being given into some other form, this is actually can be 20 or more, at least 20 times more efficient than hydrogen burning on the sun. So this is, in fact, gravitational potential energy is so far the most efficient way to extract energy, except that we don't know how to do that on Earth. But that would be the most efficient process if we could do that. So those processes combine here. Stuff is falling in, hits into the neutron star core, gets rebounded, and also as it falls in, it releases its gravitational potential energy, forms into photons that gives an outward pressure itself. And this, now essentially what happens here is that the implosion is turned into an explosion. And the explosion is so strong that it completely blows out the outer shells of the star. It's completely thrown away into interstellar space. And what you're left is with a neutron, this dense ball of neutrons, which is called the neutron star. And this whole process is called a supernova explosion, happens in our galaxy roughly once in a few hundred years or so. And when a star goes through a supernova, our sun will never become a supernova because it's not that massive, but those which are that massive, when they end as a supernova, they become so bright that one single supernova can almost outshine the whole galaxy in which it resides. And typically I'm talking a galaxy has, say, 100 or 1,000 billion stars in it. So a star can become that much brighter during this brief period, a few days, when it explodes as a supernova. But our concern here is not the supernova, but the neutron star, which is left behind here. Now let me show you from all these theoretical or schematics to a real picture. This is a picture of the Crab Nebula. It's a nebula in the direction of the constellation Taurus, and if you, on a reasonably dark night, with a small telescope, you can see the faint nebulosity in it, even with small telescopes. However, this picture here is not from small telescopes, but from some of the most flagship missions that we have. It's combined from an image taken with the orbiting Chandra X-ray satellite, which images things in X-rays, the Hubble Space Telescope, which takes pictures of astronomical sources in optical and infrared, another orbiting satellite called the Spitzer, which takes infrared images of things, and also the very large array in New Mexico, so which is a radio telescope, which is an array of radio telescopes. You can put them together and form an image. And here you see the combined image from the Crab Nebula. You can see all this nebulosity, all this gas here is from that supernova explosion, which happened in 1054 or so, documented rather well by the Chinese astronomers at that time. Here is the neutron star, this one. What it does is roughly, this is, let's say, a schematic. This line is the rotation axis about which it rotates. And it has a very strong magnetic field, the neutron star, way beyond anything that we can produce on the Earth. Many orders of magnitude more than that. And here is the magnetic axis, like for Earth also, the rotation axis and the magnetic axis do not coincide. A similar situation. You have this is the rotation axis, here's the magnetic axis. And since the magnetic field is so strong and you have a big reservoir, a big bank of particles floating around, they interact, the particles over there, the plasma interacts with the magnetic field to produce a very strongly collimated beam of radiation. It's just like you in a lighthouse. A lighthouse produces two strong, narrow beams. And as the neutron star rotates, this beam here, this is shown by red, this traces out a cone in the sky. And if you happen to lie on that cone, just like for a lighthouse, if you happen to lie on the right spot, you would see that the beam come and go by you every, whatever the lighthouse's rotation speed is. You'll see that beam come and go by you. Similar thing you do see also in neutron stars, that they kind of pulses. And that's where they get the name pulsar, pulsating stars. They were first seen in the radio because the radio observations were easier to somehow make. And this one rotates at a speed of about 30 times a second. And here is actually an audio from the Jodrell Bank Radio Telescope in Manchester, UK, where they just converted the data coming from the pulsar into audio file. And let's see if rather monotonic, but that's the sound of this pulsar. The pulse is going around. From various observations, we now know that the distance to the pulsar is about 6,500 or so light year. The neutron star that's rotating in there has a mass of about 1.4 or 1.5 times the solar mass. So that's roughly, to put in perspective, about 500,000 times the mass of Earth. And you have that much mass confined within a sphere of diameter of something like 20, 25 kilometers in size. So imagine, I think like a sphere of the size of Greater Rochester and squeezing in not only the Earth but 5,000 Earths within that. So that's how dense it is. If you could bring a teaspoonful of matter from this neutron star onto the Earth, the comparison is roughly, it would be so heavy that even one of these, the biggest oil tankers, they won't be able to carry it. It'll weigh something like 900 of the pyramids, 900 pyramids of Giza, that kind of weight, one teaspoonful of matter from the neutron star. Such dense objects these are. Now, this is a single pulsar. There's only one neutron star over here. But if we are lucky, often when stars are formed, they're not formed singly, but in pairs, let's say. In roughly what you can say what happened was initially there was a big hydrogen gas cloud which collapsed to form the stars, and not one star but two stars were formed together, which were gravitationally bound, so they go around each other. So here's a picture of, again, an artist's impression of something like that, where two stars were formed. Not two of them were the same mass. And the result of that is, the more massive the star is, this is something we know from study of stars, that the more massive a star is, the faster it goes through its life cycle. And here we have this one, which was more massive to start with compared to this. And at the time, let's say, when this picture was taken, this star was already in its later stage of life, where it had bloated up to form what we call a red giant star. So here's the red giant, and this one is slightly less massive, but still quite massive, of the order of, again, tens of solar masses. So this one is still burning hydrogen normally, and it has not bloated up. What would happen to such a binary system? So let's see. This one is a red giant phase, and then it blows up as a supernova. The outer shells are thrown off. It becomes a pulsar with its beams going around. After a while, the second star has now become bigger, a supernova, a red giant, and it starts feeding matter into the neutron star, which spins it up even more. At some time, this also blows up, forms a second pulsar. And now you have pulses from both of these going. Now, this scenario, while possible, is extremely rare. The reason is when you have one supernova explosion happening, it blows out. It's a tremendously big explosion. It blows out almost everything nearby, and there's a very good chance that the binary system in which it happened, it started, it will be broken apart. And here you need the binary to survive not one supernova explosion, but two supernova explosions. That makes it extremely rare. But still, such a system was in fact found in 2003, and which by its name is called double pulsar, because we see these pulses, the radio beam from both of these pulsars. And immediately people got very excited about it. It has an orbital period, the time it takes to go around each other, of about 2.5 hours. Orbital separation is about 300,000 kilometers or so, halfway to the moon or so. So you can imagine this is a system where there are two neutron stars of this immensely huge density moving around each other in 2.5 hours, where you basically have to go a trip to moon and come back. So they're moving very, very fast too. And these are places where you expect these GR, general relativistic effects of orbital precession, the orbit slowly changing, those things to become very strong. And these therefore become good, excellent test beds for testing GR. Just as a comparison, as I was telling before, that it takes something like 8,500 years for Mercury's orbit to precess by 1 degree due to GR alone. Whereas if you take this double pulsar, it does that in 3 weeks. So, and that was one of the first things they obviously measured for this double pulsar. And the predictions beautifully agreed with that of GR. So GR passes the precession of orbit test in this one. You can test other things here. Another thing that could be tested is, it's called the gravitational redshift. And what is happening is roughly, let's say I start climbing a mountain in the morning, and I would always be more energetic at the bottom when I start climbing. And by the time I've gotten uphill on the top, I'll be more tired. A similar thing would be expected from a photon, a particle of light that's emitted from the surface of the neutron star. So let's say this is the surface of the neutron star, and a photon is emitted here. By the time it gets out and reaches us, it loses quite a bit of its energy because it had to come out of the strong gravitational field. And you can calculate by how much it should have lost, how much energy it should have lost in the process. This test was also done for this pulsar. Without going into technical details, it agrees beautifully within 0.3% of the GR prediction. We see what exactly we should have seen. Another thing, it's called the Shapiro delay. It's again, if you have a photon that's emitted from any source, let's say, and on its way to the Earth, it has to go close to a massive object like another neutron star. And that's why this double pulsar comes into play, is you have one compact object emitting some light which goes through the potential. It goes very close to the other neutron star and then comes to Earth. What happens, what is predicted is, as it goes by near the other star, there would be a slight delay. The stream of photons will not come as they would have if this was not there. And again, these results, this delay here shows this what you would, like this, the lowest point is what you would expect if this second neutron star was not there. But because of the presence of this neutron star, at some point, so they are going around each other like this, the two pulsars. And the light from this, when you are looking at it in this position, the light which is emitted from this pulsar has to come very close to this before reaching you. And this one is delayed compared to when it was in this direction, let's say where this thing, the light from this pulsar reaches you directly. So there's a delay here. And this delay could be measured, these bars show the data, and the red line is the prediction from GR. Again, very nice agreement. One other thing that can be detected is the fact that as these pulsars go around each other in their strong field, they emit what are called gravitational waves. Now, we haven't detected gravitational waves yet directly, and there is a Nobel Prize there for who does that for the first time, a direct determination. But the indirect signature of emission of gravitational waves is that these gravitational waves will carry out some energy, and that energy will come at the expense of the rotational energy of this binary system. And what will happen is, if you started with two pulsars which were going this far apart, let's say, to start with, as they emit gravitational waves, the orbit kind of decays and they come closer and spin faster. So you would have, it's a little grayed out, but yeah, you'd start with a bigger orbit, and as you, with time, the orbit decays and then they move faster. And actually this plot shows how much the orbit has decayed. Again, well, I must say here I'm cheating a little bit. I don't know if you can read the year here. So this is time. This is time, and this is how much the orbit has shrunk in terms of second because of coming closer. Here the time starts at 1975, ends at about 2005 or so. Now, you'd remember that I told you that this double pulsar was discovered only in 2003. So how do we have observations all the way from 1975? Indeed, this is not the data from the double pulsar itself, but is from another similar system, pulsar 1913, which was discovered back in 73, 74. And actually this plot, the people who found this, they got a Nobel Prize essentially for showing this. This is an indirect evidence for the presence of gravitational waves. There was a grad student called Russell Hulse and his supervisor Joe Taylor. And this particular pulsar is known as Hulse-Taylor pulsar. And there they have a long baseline where they have observed how the period decays, and beautifully agrees with what you would predict, which is this line here. The reason I'm not showing for the double pulsar is because I was a bit lazy, and then I couldn't find the exact plot. There are plots which show that the orbital decay for the double pulsar also beautifully agrees with what you would expect from GR, but it doesn't show it in this evident form, so I sort of mixed two things a bit. But in any case, the thing is, for the double pulsar, again, this effect is so strong that what they could measure for the binary pulsar in 30 years of monitoring, for the double pulsar, they've approached and actually superseded the quality of observations in 5 or so years of observations. And for the double pulsar, they can measure the orbital decay better than 7 millimeter per day, which is quite astonishing when you think that these are systems which are few hundreds of light years away, and you're measuring a decay in the orbital period of about 7 millimeters a day or so. So these are the tests that have been performed so far, and of these, the results agree quite well, I would say, better than 0.3%. The deviation from general relativity so far is less than 0.3 if you take all these observations together. And as days go by, the precision is improving. Now, how how much time? Maybe, Emrys, do you know? Okay, maybe I'll quickly go through another rather exciting effect, which again we have all listened or heard about, is that the presence of mass causes the slight curvature in the path of light rays as they come. This again was one of the first things that Einstein predicted, and what he said was, if there is an eclipse, then the sun will be, the light of the sun will mostly be blocked, so that will allow you to see stars which are very close to the sun, which you would normally not see otherwise. But during an eclipse you can see them perhaps, because most of the sun is blocked. And what you would expect to see in that case is their positions would be slightly changed when the sun is eclipsing, the position of the nearby stars, because the light rays that are coming close to the sun will be deflected a little bit. And that formed this experiment so there was this eclipse in May 1919 or so, just after the First World War, and where the British scientists took up this challenge. Arthur Eddington was the famous astrophysicist who led this expedition. This shows the path of the totality of that 1919 eclipse. And they set up 2 observation posts, one near the coast of Africa and one over here in Sobral in Brazil, where they were observing. The plan was to take photographs of the sun, eclipsed sun, and the stars nearby, and then measure the position to see if they have indeed changed. I didn't put up the actual science results, but these are what Illustrated London News had on 22nd of November, right after the Eddington published their results, and this is what New York Times said, that there have been questions about how they analyzed their data, but at that point it was hailed as a big success of general relativity, that the amount of deflection that was indeed seen in the stars matched to what GR had predicted. While this was very cutting edge at that point, nowadays this is done almost regularly. And so this is an image taken with the Hubble Space Telescope of a galaxy cluster about 5 billion light years away. What you're seeing here is all these fuzzy patches. These are all galaxies like our own Milky Way. Each of them contain roughly a few billion, 100 billion stars in them. But what you also see is these strange things like these arcs. And what's happening here is, so these things, this galaxy cluster is in the foreground. And even behind that galaxy cluster, there is some other, let's say some other source, a galaxy or so, whose light is deflected as it comes around this cluster in the foreground. So here is our Earth here. Here is this cluster which we see, and there back somewhere is the source, the background galaxy whose light is being curved into here. And you can show that if the galaxies are extended objects, so in that case you would expect some arcs like this, and you can calculate the masses of these galaxies if you have some model and if you assume how things are. But again, that's using GR to test or to calculate the masses of these galaxies. But the fact that the bending of light is nowadays done quite regularly, it's not that big a thing. But what you should see here is these effects in both these cases really are very small. The deflection by which the position of a star is altered in the case of an eclipse is about 1.75 seconds of arc. To put it in a bit more perspective, this is something like looking at a quarter which is 2 miles away, the 2 ends of the quarter. That's how much the star will be deflected because of the presence of sun. Also in the case of cluster, the numbers are similar, very small. Are there places where these will be stronger, where the bending of light is much stronger? if you believe GR, then it says that the amount of deflection depends not just on the mass, but the mass to radius, how compact it is, mass over R. And here's one formula where the mass over R is multiplied by some constants to make it dimensionless. And if you look at this, use this formula to calculate what the compactness is of certain objects, for neutron stars and black holes, you get a number of about 1. And when you come to Sun, it's about a millionth of that. For the Earth, about a billionth. So if you want to look for strong deflections, you want to look near black holes. Now for black holes, there exists what we call an event horizon. What it says is no information can come from inside the event horizon to us. And again, as I guess as usual, I was cheating a bit while saying that this is 1. This is 1 assuming that the R is the event horizon radius. So for a black hole with an event horizon radius and mass, mass comes in through here, you will have a compactness of 1. What's the size of this event horizon? It's about 3 kilometers for a black hole which has a mass of 1 solar mass. So think about the neutron star where you had about 1 solar mass in 10 or 12 kilometer radius. Now you're down to even a factor of 4 less. You're packing in the mass of Sun in 3 or so kilometers. The radius scales linearly with mass. So instead of 1 solar mass, if you have 10 solar mass, you will have a radius of 30 kilometers. And this here shows this is the radius of the event horizon. And suppose a particle of light was emitted here. It shows how strongly the path of light will be altered as it goes near the black hole. This would test strongly what's happening near the black hole. Where do we find these black holes? As I said before, you can find neutron stars when massive stars end their life. You have the outer shell is blown out in a supernova, and what is remaining is this neutron star core. If the star is even more massive, few tenths of solar mass, then the pressure of the infalling matter is so large that you don't even stop. The core is so massive that you don't even stop at being a neutron star, but it crumples even more and forms into a black hole. So there are these 2 varieties of black holes that we definitely know exists so far. One are these which are caused by the death of stars, massive stars, which have a mass of like 10 times solar. The black holes themselves have a mass of anywhere 5, 10, 15 times the mass of the Sun. Recently, over the last few decades or so, we've found that not only there are these stellar mass black holes, but there are another variety of black holes which are found at the center of every galaxy. Almost every galaxy that we have seen seems to host, at least the nearby ones seem to host a black hole at the center. There are some controversies whether the black hole is active or not, if it's actively engulfing matter or not, but it looks like there is a black hole. And those are much more massive than their stellar mass counterparts. Their masses could start from few millions, and the most massive ones have tens of billions of masses of Sun in those black holes. And since you have in the center of every galaxy, our galaxy also, the center of our own galaxy also has one such black hole. It's not one of the bigger ones. It's actually rather small, only few million solar masses in size. But there definitely does exist one, and I'm going to show a few things just to. So here is a picture of one of the bigger telescopes, the Very Large Telescope in Chile, looking at the galactic center. This picture was taken with a normal digital camera, just by someone sitting outside the observatory. And you see the Milky Way going here, which from any place, if you go at a dark night during evenings in fall, you see this milky patch. That's the Milky Way here. What the the picture shows out is there's a lot of dust also in the Milky Way, and especially in the direction of the galactic center, which is here. Actually, this yellow beam, it's not photoshopped or anything. This is actually a laser beam which goes to the galactic, not goes, but is pointed in the direction of the galactic center. What it does, again, is a matter of another talk, but it helps to correct for atmospheric distortions. But the core of the thing is, during this time, the telescope was looking at the galactic center in infrared. You need infrared because if you look at it in optical, you are looking at dust. You can't penetrate dust in optical or visible light. And here's an image of the galactic center. The very center of the galaxy is something of the size of a full moon or so. If you could put the full moon here, it would be something of this size. This was obtained using the orbiting Spitzer satellite. In infrared, you can see the center glows. But again, this is not the glow from the black hole or near the black hole. But there are lots of very active stars very, very close to the black hole, and that gives to this brightness. You can zoom in. So the Spitzer image is rather wide-angled. You're looking at, so like the size of the moon or so, that kind of area on the sky. But when you use these other telescopes like the VLT or the Keck, you can really zoom in very narrowly onto the black hole, near the region of the black hole. And when you do that, this is an image from the VLT, which shows a region which would be just 1 light year across at the distance of the black hole. And the location of the black hole here is shown by these 2 arrows. You see there's a star over there. Again, this is not the black hole itself. The next slide will show what's going on. So this was the image of the galactic center taken in 1995. These are various stars very, very close to the black hole. Now, what we are assuming here is there's a central black hole here which is of the mass of 1,000,000 times of any of these stars, let's say. So you can imagine a situation like the solar system, right? The sun is hundreds of thousands of times more massive than Earth or other planets. And what happens is the sun sits at the center and the planets go around it. You would expect a similar situation to happen here as well, where if you waited long enough, you would see these stars would have to go around in orbits. And that's exactly what these people did. Let's see if it starts. Yeah. So with time, they got more observations and plotted the position of these stars. And they follow these orbits just like the planets do, but somewhat more eccentric. Some of them are circular, some of them come very close to the black hole and go away. But you can use these stars to measure the mass of the black hole very accurately, and that's what was done in this case. They used how long it takes for these stars. They know how massive these stars are, what are the characteristics. You can use Newton's laws here. You don't need to resort to GR at this level. That'll give you what the mass is. It turns out to be about 4 million times solar mass. The densities, again, forget the number. It's just so high that you cannot have anything other than black hole over there. Now, okay, we have proved that there is a black hole, but still, what is the size of the black hole? How close have we to see? How close do we have to zoom in to see these strong deflections that I was talking about earlier? Now, the event horizon for this black hole, as I said, the event horizon is 3 kilometers for every solar mass. So for something of 4 million solar mass, you have an event horizon size of 12 million kilometers, which may seem quite big. It's 17 times the radius of the sun itself. But you have to remember that this is 26,000 light years away from us. Now, if you take something 7 times solar radius, put it so far away, it would look as if you were, again, looking at a quarter midway to the moon at that kind of distance. So you need that kind of resolution to see. And that's way beyond anything a single telescope at present can give. So there's this ambitious project going on right now, which brings in telescopes spread across the globe, put their data together, and that will give you enough resolution to actually zoom in And these are some of the simulated images, what we might see if we could employ all these telescopes. There's one in Hawaii, one California, Arizona, Mexico, and there's the South Pole Telescope. They've already put together 3 of these. That's not enough to generate an image, but they could show that the galactic center was resolved and there were some conclusions drawn about how the shape of the emission is and so forth, but nothing like this. So to get a real image of what is happening at the event horizon, you need somewhat more ambitious. Again, this is not that far in future. Most of these telescopes, the green ones are already operational. The pink ones are midway, and this one needs another detector. So we might be looking at a time scale of few years at max before we start getting something like this. And that's more or less, I will stop today without any, so the goal is to say what's going on really near neutron stars. How right was Einstein? How much can we trust, let's say, GR to say what is happening very close to black holes and where these things start breaking down? And the ultimate goal, of course, is to understand the laws of nature, which is our hope. And I'll end at that. Thank you.